title of this section is the multiplication principle, permutations, and combinations. So it's a lot of material to cover all in one section. Let's start with the multiplication principle. If I have a series of decisions to make, and let's say there are N1 choices for the first decision, and there are N2 choices, let's call this first decision, second decision, and so on. If this is true, then the total number of ways that I can make these decisions is N1 times N2 times N3. And this could go on for as many different decisions as you have to make. Okay, this might be deciding what to wear. This could be deciding what to order at a restaurant. If you have a main dish, and then you can order a side dish, or you can order soup or salad, and a dessert and a drink. This tells you how many different combinations you could have. So let's look at an example of the multiplication principle. Suppose Angela has 9 skirts, 8 blouses, and 13 different pairs of shoes. If she is willing to wear any combination, how many different skirt, blouse, shoe combinations does she have? So to get our answer, very simple. 9 choices times 8 choices times 13 choices gives us a total of 936 different outfits. Now notice that this has the caveat that she's willing to wear any of these things, and all of her shirts and all of her skirts would go together, which usually is not the case. But just assuming that she's willing to wear anything, 936 choices. Okay, let's look at another one. Okay, this one's talking about remodeling a kitchen or putting new appliances in a new construction. In May 2017, there were 111 built-in dishwashers, 224 gas stoves, and 82 side-by-side refrigerators available for purchase at the Home Depot website. How many different ways can a homeowner outfit his or her kitchen with these 3 appliances? And again, all we do is multiply. 111 times 224 times 82 gives us a total of 2,038,848 combinations. Okay, now is this really how we buy appliances? Not usually. There's usually some things that kind of go with other things. For instance, a lot of people like all stainless steel appliances. I'm sure that would cut this number down significantly. Okay, but if I was willing to put anything with anything else, I'd have 2 million choices. Let's pause the video now and work on checkpoint 1. Next, we're going to look at sequences. Things like combination locks or symbols in Morse code, or a lot of different things like that have sequences associated with them. And let's see if we can figure out how many sequences. A combination lock can be set to open to any 3-letter sequence. How many sequences are possible? Okay, so for the first letter in my sequence, I have 26 choices. For the second letter, could it be the same letter? It could. It doesn't say it can't, so 26 choices there. And then again for the third letter, 26 choices. So altogether on this lock, I could have 17,576 different combinations. Now, what if we said that each letter had to be unique? We couldn't repeat a letter. It would change our problem just a little bit. We'd still have 26 choices for the first letter, but now for the second letter, we can't choose what we chose for the first letter again, so now I only have 25 choices. And then for the third letter, I can't choose either one of these, so now I only have 24 choices. And so this reduces my possibilities down to 15,600, which probably is still plenty for a combination lock. Let's pause the video now and work on checkpoint 2. In the next section of this lesson, we're going to look at making choices when we're not going to choose everything. And we're going to use a concept called factorial. And basically, this is factorial. N factorial is equal to n times n minus 1, let's put that in parentheses, times n minus 2 times n minus 3, all the way down to, say, 3 times 2 times 1. That's n factorial. Okay, a couple of things to remember about factorials. By definition, not n, 1 factorial is 1. Because we're taking all the integers, all the natural numbers, from n down to 1 and multiplying them. So if I'm at 1, then it's just 1. Now here's another one. This one doesn't make sense to me, but nobody asked me before they decided that 0 factorial is also equal to 1. Okay, I don't know how they came up with that, but we just got to remember it. So that's factorial. Let's work a couple problems with factorial. A lot of times we have 1 factorial divided by another factorial. For instance, 100 factorial divided by 98 factorial. Okay, and I know you're hoping that we don't have to do 100 times 99 times 98 times 97 all the way down to 1, and then turn around and do 98 times 97 times 96 all the way down to 1. And we don't, because this is a fraction, and I know I can reduce a fraction by eliminating common terms in the numerator and the denominator. So in this instance, I've got a 98 here and a 98 here, so those are gone. 97, 97, those are gone. I didn't write 96 up here, but I could have. And all the other numbers less than this are all going to cancel out. So what's left? 100 times 99, which I can do in my head. Okay, times 100 means add 2 zeros, so 9,900. Okay, so factorials sound like it's a lot of work, but they really aren't. Let's look at another one. This time I'm going to have 3 factorials in my expression. I've got 5 factorial divided by 2 factorial times 3 factorial. Okay, and this is a fairly common structure that we use in permutations and combinations, where I have a number up here and then I split it into 2 numbers that add up to that number on the denominator. Well, this is pretty small. Let's write it out. 5 times 4 times 3 times 2 times 1 divided by 2 times 1 times 3 times 2 times 1. And so I can see immediately that the 3 2 1s are going to cancel out, which means that I could have written 5 times 4 times 3 factorial over 2 factorial times 3 factorial. And these factorials are just factors. So I can cancel them out like that. Now I'm left with 5 times 4 over 2, because I don't really need the 1. And that's easy enough, 20 divided by 2. But if I had some larger numbers, I could look at 4 and say, well, 4 over 2, I could cancel out and just leave a 2, and then I have 5 times 2. The whole denominator is gone, so this is just 10. Let's pause the video now and work on checkpoint 3. Now we're going to talk about Morse code. Morse code is something that was developed for use on the early telegraphs. It was also used with flashing lights on ships at sea to communicate quickly and clearly before the advent of good voice communications. So Morse code uses a sequence of dots and dashes to represent letters and words. How many sequences are possible with at most 3 symbols? So for every piece of the Morse code, we have 2 choices, a dot or a dash. So if I had 3 symbols, I could have 2 choices for the first symbol, 2 choices for the second symbol, 2 choices for the third symbol, for a total of 8 choices. Now if I had only 2 symbols, it would be 2 times 2, so that would be 4 more. If I had only 1 symbol, it's either a dot or a dash, so that would be 2. And altogether this gives me 14 symbols. Well, I have 26 letters in the alphabet, so 14 symbols is not enough, which means that some of my letters are going to have to be represented by 4 symbols. And if you look at Morse code, a lot of the letters that are used less frequently are the ones that have 4 symbols, so that it's a little quicker. The letters that are used very often tend to have the shorter sequences. So let's see what happens if I had 4 symbols. 2 times 2 times 2 times 2 gives me 16. If I put that with the 14 I had before, now I have 30, which will give me all the letters and 4 left over for other things. Okay, so that's a little bit about Morse code. Let's pause the video now and work on checkpoint 4. Next, we're going to talk about permutations. And permutations are sets of symbols that are in a particular order. Okay, for instance, words are permutations. If I had the letters A, C, and T, and I arranged them that way, you would recognize that as the word act. If I switch the A and the C, it's cat. And these are not the same thing. And of course, if I put the T first, and then the C and the A, it doesn't make a word. Okay, so in permutations, order is important. Well, let's leave that up there, because we've already made 3 different arrangements. Let's see how many others we can make. This started with A. If I start with A and then switch the other 2 letters around, I get that. This started with C. I could do C, T, A. And this started with T, so I could do T, A, C. So these are all the permutations of these 3 letters. So there are 6 permutations of 3 letters. Okay, that's all the possible arrangements of those 3 letters. Okay, let's look at something that's a little more real life. And let's talk about baseball, batting order. How many batting orders are possible for a 9-person baseball team? We're assuming that we're going to use everybody we've got. Well, for the first position, or the leadoff batter, I have 9 choices. And after I've chosen that person, for the second batter, I only have 8 choices. And then I have 7 choices. And all the way down, does this look familiar? Okay, so for my 9-person baseball team, this is how many choices I have for the batting order. And when I multiply that all out, I get 362,880. Well, with that many choices, you would think, well, we could have a different batting order every day. But they don't. Why don't they have a different batting order every day? Because there are some places in the batting order where certain skills are more important than others. For instance, the first batter, the leadoff batter, they want that to be a pretty good hitter because it just helps to get things rolling. The 4th batter is called the cleanup batter. And the idea is, if I put some of my best hitters up here, I have a high chance of getting them on base, and then the cleanup batter, hopefully would hit a home run or at least a double and get some of those folks home. Okay, who bats at the end? Well, if you're in the National League, usually that is the pitcher. Okay, pitchers aren't known for being really good batters, so we put them at the end so that as we go through this order over and over again, maybe they're not going to get called on as many times as the other batters. So we leave them at the end. But this is what I could do if I wanted to. The general, we don't want to. And the other thing with this is that baseball players tend to feel more comfortable if they're in the same place in the batting order on a consistent basis. Okay, let's change this up a little bit and look at a set where we don't choose everything in the set. A teacher has 5 books and wants to display 3 of them side by side on her desk. That maybe is all the room she's got. How many arrangements of 3 books are possible? So now we're going to look at, for the first book she chooses, she's got 5 choices. When that book has been decided, now she has 4 choices for the second book and 3 choices for the third book. So this gives her a total of 60 choices for those 3 books. And remember when we said we had 3 letters and there were only 6 different combinations? Because we used them all. Here, when we don't use everything, we end up with more choices. Let's pause the video now and work on checkpoint 5. In that last example, we had a teacher who was choosing from a set of 5 books, but was only going to choose 3 of them. And we call that a permutation. And there's a couple ways that we can write this. A lot of times we write it this way. Permutations of 5 things taken 3 at a time. Okay, you might also see, this is what your book uses, but you might also see it this way sometimes. Okay, these mean the same thing. And those are permutations. Okay, and the number of permutations, if I'm going to take the whole set, everything in the set, for instance, if I'm going to take the permutations of 5 items 5 at a time, that's equal to 5 factorial. Because I'm going to take 5 and then 4 and then 3, 2, and 1. Okay, so permutations of 5 things, or n things taken n at a time, is n factorial. Now, if I'm not going to take all of the elements, my formula is a little more complicated. So we say the permutations of n things taken r at a time is going to be n factorial. So that part's the same, but now we're going to divide it by n minus r factorial. So let's think about our books again. If I had 5 books, this would be 5 times 4 times 3 times 2 times 1. Well, I know that the 2 and 1 don't belong up there. So I have n minus r, so 5 minus 3 is 2. So I have 2 factorial in the denominator, which cancels out those last 2 numbers that I don't want. So this is the formula for permutations. I know most of you are probably pretty tired of hearing about the elections, but we do have a election-related problem here that we can solve with permutations. It says, early in 2016, 12 candidates sought the Republican nomination for president at the Iowa caucus. The Iowa caucus is one of the very first chances that they get to collect some votes. In a poll, how many ways could voters rank their first, second, and third choices? Well, there's 12 candidates. So I'm going to have 12 candidates, but I only get to choose 3. Okay, so you could do this way. 12 times 11 times 10, and just do it that way. Or you could do 12 factorial over 12 minus 3 factorial, if you remember this formula. And of course, this is just the same thing. 12 times 11 times 10 times 9 factorial over 12 minus 3 is 9. So 9 factorial here, and I cross those out. 12 times 11 is 132. The 10 makes a 0 at the end. So 1,320 ways to rank your 3 highest candidates. Let's pause the video now and work on checkpoint 6. We can also use permutations when we have more than one group that we're choosing from, as in this situation. In a college admissions forum, 5 female and 4 male sophomore panelists discuss their experiences with high school seniors. In how many ways can the panelists be seated in a row of 9 chairs? Okay, this is the basic permutation. In the first seat, I have 9 choices, then 8 choices, then 7, on and on and on. So this is 9 factorial, which is the 362,880. However, what if I said that the males and the females were to be alternated? Well, that means that I have to start with a female. So now I only have 5 choices for the first seat. Second seat has to be a male. There's only 4 males to choose from. After I've chosen that first female, now there's only 4 females to choose for the third seat. And we're going to continue in this pattern until we end up with the last male and then the last female. And when we multiply that all out, we're down to 2,880. So if you look at that, we've eliminated 360,000 arrangements by specifying that it has to be male, female, male, female. Okay, and now, what if we say we're going to put the males on one side and the females on the other side? Now we need to do 2 permutations. Okay, so for the females, it's 5 factorial. We have 5 females, and so we can have 5 factorial different arrangements of them. We have 4 males, and so we have 4 factorial different arrangements for the males. Then we go back to our multiplication principle. If I have 5 factorial ways to do this, and 4 factorial ways to do this, then I have to multiply those 2 to get my answer. So 5 factorial, 5 times 4, 3, 2, 1. And here, 4 times 3 times 2 times 1. Well, let's see. These numbers look a lot like these numbers, just in a different order, which for multiplication wouldn't matter. I've got 5s that match up. This 4 could be matched. This 4 could be matched. 3, 3, 2, 2, 1, and 1. So I can see that whether I say it has to be female, male, female, male, female, male, or all the females and all the males, I still have the same number of arrangements. And that would be the 2,880. There is one more little thing though. It doesn't say that the females were going to be on the left and the males were going to be on the right. So if I switched it, I would actually double this number. 2880 times 2 would give me 5,760 different arrangements if I group the students by gender. Pause the video now and work on checkpoint 7. Let's think back a few examples to the teacher who was choosing 3 books to display on her desk out of a set of 5. In that example, the order made a difference. But if we change that problem up a little bit and say the teacher's picking 3 out of the 5 books to donate to a charity auction, then the order is no longer important. It's just sets of 3 books. So if we go back to where the order was important, we had 5 books to choose for the first one, 4 for the second one, and 3 for the last one. But recall that since the order is not important, think about when we looked at the 3 letters, and we said there were 6 ways to rearrange those 3 letters. So I'm going to divide this by 6 because I don't care about the particular order of the group. And I'm actually going to rewrite that 6 as 3 factorial. So now I could write this as 5 factorial divided by 3 factorial, but that 5 factorial also has a 2 times a 1, so I can put that down here, 2 times 1. Okay, and you might also recognize that as something we did in one of our other examples. Okay, when we're looking at choosing a group where order is not important, instead of calling that a permutation, that's called a combination. Now let's look at that again. 5 times 4 times 3 divided by 3 times 2. Well, this was 60 divided by 6. There's only 10 ways for the teacher to choose 3 books out of her set of 5 to give away. And just like we use a P for permutations, we're going to use a C for combinations of n things, taken r at a time. And our formula looks like this. N factorial divided by n minus r factorial times r factorial. Combinations are useful in situations like choosing committees. If I'm choosing a committee and I don't care what order, if there's no positions on the committee, everybody's equal on the committee, then I don't care about the order in which I choose them. So if I had a group of 10 students and I'm choosing a committee of 3 to meet with the dean, I could write it as the combinations of n things taken r at a time is equal to, our n is 10 and our r is 3. 10 students, we're going to pick 3 of them. So this is going to be 10 factorial n minus r. 10 minus 3 is 7 factorial, and then the r would be the 3 factorial. If I need to actually work this out, I could do it this way. 10 times 9 times 8 times 7 factorial. When I get to the largest factorial in the denominator, that's where I stop. So I'm going to put the 7 factorial here and the 3 over here now. These cancel out. And I know that 3 factorial is 3 times 2 times 1. And the 1's not going to affect the value, so I'm going to write just 3 times 2. Now, how can I reduce this? 9 divided by 3, I could reduce that by a factor of 3. 8 divided by 2 could give me just a 4 up here. So now I have 10 times 3 times 4, which gives me 120. So I have 120 different committees that I could choose. Let's look at another form of committee. Let's look at choosing a jury. They always have more people available than they need to seat a jury because of people being excused for various reasons. So if I have 40 people, and I need 12 to form a jury, not 12 juries. Again, I don't care about the order at this point. I just need to find 12 people. So I'll take the combinations of 40 people taken 12 at a time to find out how many different juries I could form. So it's going to be 40 factorial divided by 40 minus 12 is 28 factorial times 12 factorial. Okay, we use the same principle here that we did before. We're going to multiply from 40 down to 29. The 28 factorial we're going to eliminate, and then we'll have 12 factorial still in the denominator. At this point, these are a few more numbers than we've worked with before in larger numbers. So at this point, I would use a calculator to calculate this. And even with eliminating the 28 factorial, we end up with 5,863,480 possible juries. Pause the video now and work on checkpoint 9. Here's another problem involving combinations. 3 managers are to be chosen from a group of 30 to work on a special project. In how many different ways can the managers be selected? Well, this is pretty straightforward. We've got 30 managers and we're going to choose 3. So this would be 30 factorial over 27 factorial, 30 minus 3, times 3 factorial. So I'm going to have 30, 29, 28, 27 factorial over 27 factorial And now I need the 3 times 2 for the 3 factorial. Okay, probably the easiest way to reduce this 3 times 2 is 6, so 30 divided by 6 is 5. I'll have 5 times 29 times 28, which gives me a total of 4,060. So if I just need to pick 3 managers out of this group, I could pick 4,060 different groups of 3. Now let's change it up a little bit. Let's say that the special project was actually thought up by one of the managers, and he's insisting he needs to be on the project, which is probably a good idea. So now I've eliminated one of the managers from the group. I've also eliminated one of the managers from the selection. So now I'm going to take the combinations of 29 remaining managers, but I'm only going to choose 2. So this is going to be 29 factorial divided by 27 factorial times 2 factorial. So 29 times 28 times 27 factorial over 27 factorial times 2 factorial, which is just 2. So I'll get rid of the 27s. 29 times 28 divided by 2 gives me 406 ways to pick the 2 remaining managers. Now let's switch it up again. Let's say that I can't have any more than 3 people working on this project, but perhaps I could have 2 or even just 1. Now, how many ways could I pick the group for the project? We've seen now that we can pick from 30 managers 3, and we came up with 4,060 ways to do that. But if I'm only going to pick 2, that would be 30 factorial over 28 factorial times 2. So 30 times 29 times 28 factorial over 2 times 28 factorial. So 30 times 29 and then divided by 2 gives me 435. So let's put those two numbers together. 4,060 3-person groups, 435 2-person groups, and if only one person is going to be chosen, it just makes sense that that's only going to be 30 ways to do that. So when I add this all together, I see that there are 4,525 ways to pick a group of either 1, 2, or 3 people to work on this project. Pause the video now and work on checkpoint 10. We've talked about 2 things in this section that can often be easily confused. And it's important that you understand when you should use each one. So let's look at some examples of situations and decide whether we should use permutations or combinations. Okay, the first situation, how many 4-digit numbers are possible if no digits are repeated? Well, if I'm making a 4-digit number, then the order is important. So for part A, 4-digit numbers, I need permutations. Part B, a sample of 3 light bulbs is randomly selected from a batch of 15 bulbs. How many different samples are possible? Well, if I'm picking a sample, the order in which I choose the light bulbs is not important. So for B, which is light bulb sample, combinations would be useful. In the next example, in a basketball conference with 8 teams, how many games must be played so that each team plays every other team exactly once? Now this is the beginning of setting up a schedule. We're just trying to figure out which games need to be played, but the order at this point is not important. So for C, for basketball games, we would use combinations. Okay, later on, if we're trying to set up the schedule, then the order might become more important. But at this stage of the planning, combinations are adequate. And then part D, in how many ways can 4 patients be assigned to 6 hospital rooms so that each patient has a private room? Okay, for this example, assigning a patient to a particular room is an ordered selection. For instance, let's say I have rooms 1, 2, 3, 4, 5, 6, and I assign the first 3 patients to rooms 1, 2, and 3. Assigning the last patient to room 4 is a different arrangement than assigning the last patient to room 5. So in this case, order is important, and we need to use permutations. You're going to solve all these problems in checkpoint 10. You're going to solve all these problems in checkpoint 11. This example is another instance where permutations or combinations might be used depending on the specific circumstances of the situation. A manager must select 4 employees for promotion. 12 employees are eligible. In how many ways can the 4 employees be chosen? Well, all 4 employees are going to be promoted and doesn't say anything more about it. And so the order doesn't seem to be important for this situation. So I would use combinations of 12 people taken 4 at a time. I've got 12 factorial divided by 8 factorial times 4 factorial. So we'll do on the top 12, 11, 10, 9, 8 factorial, and underneath 8 factorial, 4, 3, 2, 1. So the 8 factorials are gone. 4 times 3 is the same as 12. And then we could take 10 divided by 2 and make that a 5. So now I have 11 times 9 times 5. 11 times 9 is 99. Times 5 would be 495. So if I'm just going to pick 4 employees to be promoted, I could make 495 different groups of 4. However, if I'm going to choose these 4 employees and place them in 4 different specific jobs, now order becomes important. So for this problem, I need to use permutations. And so using my permutation formula is just 12 factorial over 8 factorial. I'm just going to have left on the top 12, 11, 10, and 9. And the 8 factorial here will go away with the 8 factorial that's left up here. And so for this, because the order is important, I have 11,880 ways that I can choose the employees for these 4 specific jobs. Pause the video now and work on checkpoint 12. I know in this chapter that we've looked at several different casino games, and now we're going to look at Powerball. And it's not my intention to teach you how to gamble, but in this example particularly, it's my intention to show you how much you're gambling and how small your chance of winning is. So we're going to talk a little bit about Powerball. Powerball is a lottery game played in 44 different states and 3 other areas. For a $2 ticket, a player selects 5 numbers from 1 to 69 and 1 Powerball number from 1 to 26, which may be the same as one of the first 5 chosen. A match of all 6 numbers wins the jackpot. How many different selections are possible? So let's look first at the 5 numbers. I've got to pick 5 numbers from 1 to 69. So for the first number, I have 69 choices, and then 68, 67, 66, and 65. 2, 3, 4, 5 numbers. And now I can pick a Powerball number, and I have 26 choices for the Powerball number. That's a lot of numbers to multiply. Another way we could write this, we could say 69 factorial over 69 minus 5, so 64 factorial times 5 factorial, and then times the 26 choices for Powerball. And this comes out to 292,201,338 different ways to pick these 6 numbers. So when you pick the 6 numbers, you have a 1 in almost 300 million chance of winning the Powerball. Pause the video now and work on checkpoint 13. Okay, we've pretty much come around full circle now. We're going to go back to choosing clothes, but do it just a little bit differently now by choosing just a part of all the clothes that a person owns. A male student going on spring break at Daytona Beach has 8 tank tops and 12 pairs of shorts. He decides he will need 5 tank tops and 6 pairs of shorts for the trip. how many ways can he choose the tank tops and shorts? So this is a combinations problem. The order in which the clothing is chosen is not important. So we're going to have the combinations of the 8 tank tops, taken 5 at a time, and the combinations of the 12 pair of shorts, and we're going to take 6 of those. So this is going to be 8 factorial over 5 factorial times 3 factorial. So this is 8 times 7 times 6 times 5 factorial over 5 factorial times 3 times 2 times 1. So these go away. 6 is equal to 3 times 2, so those can go away, and the one we never needed. So there are 56 ways to choose tank tops. Now let's look at the shorts. 12 factorial over 6 factorial times 6 factorial. So I've got 12, 11, 10, 9, 8, 7, 6 factorial over 6, 5, 4, 3, 2, 1 times the other 6 factorial. Those cancel out. And when I work this all out, I end up with 924 ways to choose shorts. Now I have to use my multiplication principle again and multiply 56 ways to choose tank tops times 924 ways to choose shorts. And I have a grand total of 51,744 ways to choose clothes for the trip. Decisions, decisions. I could spend all my spring break trying to figure that one out. Or I can just throw stuff in the bag. Okay, pause the video now. Work on checkpoint 14. Well, we made it. This has been a long lesson, but this is the last example. To illustrate the differences between permutations and combinations in another way, suppose 2 cans of soup are to be chosen from 4 cans on a shelf: noodle, bean, mushroom, and tomato. We can draw a tree diagram to show there are 12 ways to select 2 cans from the 4 cans if the order matters. So let's do that. For our first can, we've got 4 choices. We're calling them noodle, bean, mushroom, and tomato. And now we're going to say, if I chose noodle first, now I have 3 choices. I can choose bean, mushroom, or tomato. If I chose bean first, I could choose noodle, mushroom, tomato. If mushroom was first, then I could do bean, noodle, and tomato. And if I chose tomato first, I could have noodle, mushroom, or bean. So now I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So 12 ways if order matters. Okay, but if order doesn't matter, then my diagram becomes much simpler. My first choice, I still have noodle, bean, mushroom, and tomato. And then my second choice here could be bean, mushroom, or tomato. But my second choice here, noodle bean, would be the same as bean noodle, so I don't have that choice. It's just mushroom or tomato. And if I choose the mushroom first, then my second choice here, I already have bean mushroom and noodle mushroom, so I can have mushroom, tomato. And for tomato, if I chose tomato first, I've already listed all the different combinations: tomato with mushroom, tomato with bean, tomato with noodle. So there's no additional choice there. And so now I have only 6 choices if I don't care about the order. So just another way to think about permutations and combinations. Okay, you should be ready now to go on to your homework assignment and then on to your unit test.